The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. So today we're going to be wrapping up the last chapter, chapter 11. We're going to cover 11.6 and 11.7, and then your homework will be 11.6, 11.7 in the review. Tomorrow we'll review, and then on Wednesday you'll take your chapter 11 test. Thursday and Friday we'll review for the final exam, which is the following Monday, so a week from today. Okay, are there any questions from the homework over the weekend from 11.5 that you'd like me to look at before we go on?
Yes, I have some.
All righty, what do you got?
So it's the last one. To estimate the number of hours T that a murder victim had been dead, a coroner used the formula, and then it's T equals 1 over 0.25, and then ln 98.6 minus TS over.
Is the ln on top or up front?
Up front. It's just a 98 and then, yeah.
Okay.
Over 82 minus T and then the S. And then.
Like that?
Yes. And then it says where TS is the temperature of the surroundings where the body was found if the crime took place in an apartment where the thermostat was set at 75 degrees, approximately how long ago did the murder occur? And then round to the nearest decimal place.
Okay, so I've got the formula written correctly.
Yes.
And then T of S is 75. So then T equals 1 over 0.25 natural log of 98.6 minus 75 over 82 minus 75, which is, let's see, 1 divided by 0.25 would equal 4. Okay. And then the natural log of, let's see, we've got 98.6 minus 75 would be 23.6, and 85 minus 75 would be 7. So we've got 4 times the natural log of the quantity, 23.6 divided by 7, and I'm getting, oh, T is the number of hours, right?
Yes.
I was thinking it was the temperature, and I'm getting 4.86, and I thought, oh, that can't be right. So into the nearest 10th?
Yes.
So I get 4.86, so it'd be 4.9 hours. Put that in and see if that's correct.
Yes, it is. Thank you.
You're welcome. Any other questions?
No, I can do the rest of them. Thank you.
Okay, anybody else? Anything from 11.5 before we go on?
No, I'm okay.
Greg, you okay?
Yeah, I'm good.
All right, so we're going to go on to 11.6, and to kind of introduce that, a while ago I said this. I said 2 to the 3rd power was 8, 2 to the 4th power was 16, and 2 to the x was, and I can't remember what number we used. Let's go with 11. Okay, doesn't really matter as long as it's some number between 8 and 16. All right. And then I said, well, 2 to the x equals 11 could be changed to log base 2 of 11 equals x. The problem with that, we've learned about log base 10, or log, and log base e, or ln, natural log, but we haven't learned about log base 2, how to deal with that on our calculator. Now, some scientific calculators actually have a button that I think is log, and then it has a little box there and a little box there. So some scientific calculators, you can put this in directly, but most of them you can't. So what we need to use is something called the change of base formula. And that's all we're going to look at in section 11.6. Okay. So in 11.6, there's a formula called the change of base formula. It's on page 969 in the textbook. I don't know about the ebook, but the formula looks like this. It says log base b of some quantity x equals log base a of x divided by log base a of b. Now, what about base a? Well, we want to use either base 10 or base e because those two we have in our calculator. Okay, so let's take this equation, x equals log base 2 of 11. I could rewrite that log base 10 of 11 over log base 10 of 2, or the natural log of 11 over the natural log of 2. And I get the same answer for either one. But I've got to use either base 10 on top and bottom or base e on top and bottom. All right, so let's see. Log of 11 divided by log of 2, and I'm getting 3.45943. And then if I use natural log of 11 divided by the natural log of 2, I get the exact same answer. Now, you got to be careful. Don't use like log base 10 on top and log base e on the bottom. They've got to both be 10 or both be e. All right. So let's look at some more examples of that. And have you, if you have a calculator handy, you can try it. If we want the log base 7 of 3, using the change of base formula, using base 10, that would be the log of 3 divided by the log of 7. Log of 3 divided by log of 7, and you should get 0.56457, so 48. Or you could use natural log of 3 over natural log of 7. And you should get the exact same thing. Do you need more examples of that?
No.
No.
All righty, then we'll go on to section 11.7. Again, all we're doing in 11.6 is that one change of base formula. Okay. All right, we're going to look at some things that we've actually done before, and then we're going to expand on that. Let's say we have the equation 3 to the x plus 1 power equals 27, and we are to solve this equation. All right, we talked about before, I believe, where if we had an equation and we had a base to a power equals a base to a power, if the bases were equal, the powers were equal, and vice versa. So what I can do here, I could rewrite 27 as 3 cubed. So now I have 3 to some power equals 3 to some other power. So the equation now becomes x plus 1 equals 3. In other words, I can set the exponents equal. And from there, I can solve the equation x equals 2. So 3 to the 2 plus 1 equals 27, 3 cubed equals 27, 27 equals 27, and it checks. Are you okay with that?
Yes.
All right.
Yeah.
Let's say we've got 8 to the negative 2x plus 1 power equals 1 over 64. So 8 to the negative 2x plus 1 equals 1 over 8 squared. 8 to the negative 2x plus 1 equals 8 to the negative 2 power. So now I have the same base, so we can set the exponents equal. Solving for x, subtract 1, negative 2x equals negative 3, divide by negative 2x equals 3 halves. Check your work. 8 to the negative 2 times 3/2 plus 1 would be 8 to the -3 plus 1 would be 8 to the -2. And that would be 1/64 equals 1/64. So it checks. So far, so good?
Yes.
All right, now, what about this? 7 to the x power equals 12. Well, the problem here is, I don't know about you, but I can't think of a way to take 12 and write it as 7 to some power easily. I don't know how to do that. And I don't know how to take 7 and write it as 12 to some power. But what I do know is how to play baseball. That is, how to take this exponential equation and change it into a logarithmic equation, right? We can do that. Remember that little ditty?
Yes.
I'm going to rewrite that and just put the x on the left so that I can now take this part of the equation and apply the change of base formula to it. Aha. So log of 12, close it up, divided by log of 7, close it up, and I get 1.27698. We're going to round to 4 places. The 8 would round up, so 1.2770 is approximately the answer. So 7 to the 1.2770 power should be approximately 12, not exact because we did round off. So we changed an exponential equation to a logarithmic equation, then we used the change of base formula to get the answer. Any questions on that?
No.
All right.
No.
Good, 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 good. Here's another example. E to the 3.3 t power equals 9.1. Well, again, I don't know how to take 9.1 and write it as e as some power. So I'm going to change this exponential equation into a logarithmic equation, which would be log base e of 9.1 equals 3.3 t. However, isn't log base e just natural log? So I've got the natural log of 9.1 equals 3.3 t. To solve for t, I'm going to divide both sides by 3.3. So t equals the natural log of 9.1, the whole thing divided by 3.3. Now, it's the natural log of 9.1 divided by 3.3. It's not the natural log of 9.1 divided by 3.3. In other words, you're going to close that up before you divide to get that in the denominator. Okay, so natural log of 9.1, close it up with parentheses, divided by 3.3, and I get 0.66917, so 0.6692. Okay with that?
Yes.
All righty. Let's say we've got this situation. Log of 5x equals 4. Solve the equation. Well, here is an equation that's in logarithmic form. What's the implied base here? What base are we in?
10.
Good. So now, changing this to an exponential equation, it would be 10 to the 4th equals 5x, which is 10,000 equals 5x, divide by 5, and x equals 2,000. So we're taking exponential equations and putting them in logarithmic form to solve them, logarithmic equations and putting them in exponential form to solve them. Recall the other day I warned you, I said about 99.9% of the time, that's what you tend to end up doing. All right. How about this one? Log of the quantity 3 minus 2x equals log of the quantity x plus 24. Well, just like if they have the same base, if both sides of the equation, if they're both sides are a log to the same base, we can take these quantities and set them equal to each other. So our equation becomes 3 minus 2x equals x plus 24. I'm going to solve for x on the left. 3 minus 3x equals 24. Subtract 3. Negative 3x equals 21. Divide by negative 3x equals negative 7. Let's see. Negative 2 times negative 7 would be 14 plus 3 is 17. And negative 7 plus 24 would be 17. The log of 17 equals the log of 17. So it checks. Okay with that?
Yes.
All right. Let's see here how we're doing. Okay, let's go to story problems. And there are a couple of formulas that I want to introduce. Let's see here. Where is that one? Did I already introduce the doubling formula? T equals a natural log of 2 over r.
No.
I don't remember that.
Yeah, I think that was back. Yeah, that's back at 11.5. So yeah, I did introduce that. Let me just reiterate it here. So T equals a natural log of 2 over R. That was a shortcut where if we had a population and we wanted to know how long it would take to double it, if we knew the
Yes.
growth rate, remember that?
Yes.
Okay. I just couldn't remember whether we already covered that because I've done this all in the other class. So that's a little confused here Monday. All right. So new formula we're going to look at is called the half-life formula. And what I want to point out, I'm actually going to come back to this formula in a minute. If we have y equals 2 to the x power, that's going to look something like that, right? The base is greater than 1. It's going to increase. If we have y equals 1/2 to the x power, the base is less than 1. It's going to decrease, okay?
Yes.
But what if I had y equals 2 to the negative x power? Wouldn't that be the same as y equals 1 over 2 to the x power?
Yes.
Yes.
Okay. And isn't 1 equal to 1 to the x power? Because no matter what exponent you put in there, you're going to get a 1.
Yes.
So this would be equal to 1/2 to the x power. My point is this. This thing here is equal to that. So here it's increasing, but the same base with a negative exponent makes it decrease. Why am I taking you through all of that? Okay, let's go back to this formula. They could have written it like that. In fact, if it had been up to me, I would have, but they didn't. They used a base of 2, but a negative t as an exponent. So this is actually a decreasing formula, okay? And it's decreasing at what rate? Well, at half. So it's a half-life formula. Now, how does that work? Let's say that we had 64 Snickers bars in a refrigerator. And we came back 1 week later, and half of them had disappeared. There were 32 of them. And then we came back 1 week later, and half of them had disappeared. So there were 16 of them. And we came back 1 week later, and half of them had disappeared. So there were 8 of them. Now, half of the amount at the starting time. So half of 64 is 32. Half of 32 is 16. So we're not losing 32 1 week and 32 the next week. Each week, we're losing half of what is there at the beginning of that week. Okay, so the half-life for the Snickers bars would be 1 week. In other words, every week that goes by, half of those Snickers bars are disappearing. Okay, now with radioactive material, the theory is there's this idea of half-life that if you know what there is to start with and you know the half-life, then after that much time goes by, half of the original amount should still be there. Likewise, if you know the original amount and then you know how much is there at a given time, you can determine basically how old that object is. Okay. All right. Now, so this is going to be our new formula. And let's take a look at some examples. This first example says tritium decay. I'm not sure what tritium is, but it says the half-life of tritium is 12.4 years. So the half-life, that's H, is 12.4 years. So every 12.4 years, half of what was there to start with disappears. How long will it take? So the time is the unknown, for 25% of a sample of tritium to decompose. All right. Now, our formula is A equals A sub 0 times 2 to the negative T divided by H power. All right. See if I can write that a little bit better here. Nope, come on. There we go, finally. We have a problem. Let me read it again. It says the half-life of tritium is 12.4 years. So we know the half-life. How long will it take? Time is the unknown, but it says for 25% of the sample to decompose. They don't tell us how much is there at the beginning. So we're just going to say there is A sub 0 there at the beginning. But it says, how long will it take for 25% to decompose? Well, if 25% decomposes, how much is left? If you have 100% of something,
75.
right. So the final amount is 75% of the starting amount. So A equals 0.75 times A sub 0. So I really don't even need to know the starting amount. I just know that we lost 25% of it. So the ending amount is 75% of the starting amount. Everybody see that, where the 0.75 came from?
Yes.
So now our equation becomes this. 0.75 A sub 0 equals A sub 0 times 2 to the negative T divided by 12.4 power. All right. My next step is going to be to divide both sides by A sub 0. So then I get 0.75 equals 2 to the negative T over 12.4 power. I have an exponential equation. I'm trying to solve for the variable that's in the exponent. So I'm going to change this exponential equation into a logarithmic equation. So it's going to become log base 2 of 0.75 equals negative T divided by 12.4. See how that works?
Yes.
Good. To solve for T, I'm going to multiply both sides by negative 12.4. Why negative? Because I've got to get rid of that negative in front of the T. So negative times negative is positive, and the 12.4s will reduce out. So now T equals negative 12.4 log base 2 of 0.75. But I can't put that into my calculator without using the change of base formula. So this becomes negative 12.4. I'm going to use log base 10. So the log of 0.75 divided by the log of 2. And now it's calculator time. So negative 12.5 log base 10 of 0.75, close it up, divided by log base 10 of 2, close it up. And I get 5.187968741. Let's see, we're gonna round off to the nearest 10th. So that would be approximately, hang on here. Okay, what did I do wrong here? Oh, I see what I did wrong. I put 12.4 in instead of 12.5. That's what I get for not looking closely enough. So this should be negative or 5.146464991, which round off to the nearest 10th becomes 5.1 years. Okay, so the 4 would round down. Sorry about that. Like I said, I put a 5 in there when I should have put a 4 in. Calculator error, operator error. Okay, you all right with this problem? Any questions?
I'm okay, thank you.
All right, let's take a look at, let's see here, this one. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had that it is assumed to have had initially. How old is it? All right, carbon-14 is one of these radioactive substances, so we're talking about the half-life formula. So A equals A sub 0 times 2 to the negative T over H power. So we've got H, T, A sub 0, and A. A bone fragment analyzed by archaeologists contains 60% of that which it's had initially. So we don't know the initial amount, but the ending amount, it doesn't lose 60%. In the previous problem, it said that it lost 25%. This one says it contains 60%. So A is going to be 60% of the original amount. So you've got to read the problems carefully. Some of them tell you how much goes away. Some of them tell you how much is left. It's not meant to trick you, but you've got to read it carefully. All right? Are we okay where I got the 0.6 A sub 0?
Yes.
Now it says, it tells us in a previous situation that the half-life of carbon-14 is 5,700 years. So time is the unknown. So our equation looks like this. 0.6 A sub 0 equals A sub 0 times 2 to the negative T divided by 5,700 years. The next step is divide both sides by A sub 0. So 0.6 equals 2 to the negative T divided by 5,700 years. The next step is to change it into a logarithmic equation. Log base 2 of 0.6 equals negative T over 5,700. The next step, we're going to multiply both sides by negative 5,700. That's going to give us T equals negative 5,700 log base 2 of 0.6. Using the change of base formula, T equals negative 5,700 log 0.6 over log of 2. And again, I could be using natural log, I just don't. So negative 50, oops, turn it on, negative 5,700 log of 0.6, close that up, divided by log of 2, close that up, and I'm getting 4,200.703, et cetera, and we're going to say about 4,200 years. Okay. Any questions on that?
No.
No.
Okay.
No.
Let's take a look at this one. Let's see here. Compound interest. If $1,300 is deposited in a savings account paying 9% interest, compounded quarterly. How long will it take the account to increase to $2,100? Okay, so my question is this. Let me read it to you one more time. If $1,300 is deposited in a savings account paying 9% interest, compounded quarterly, how long will it take the account to increase to $2,100? Which of these two formulas are we going to use? The first one or the second one?
Second one?
Hmm,
No, the first one?
why?
I don't know. I took a guess.
Okay, because it says compounded quarterly. This one is used if it's compounded continuously.
Oh, yeah. See, I heard compound and my head immediately went to the PERT one, but
Ah.
that I didn't know the specific reason.
Quarterly, quarterly, quarterly. All right. So if it's anything other than continuously, we're going to use this first formula. So let's see. We've got $1,300. Paying 9%, compounded quarterly. How long will it take to reach $2,100? Okay. Now, I can take 0.09 divided by 4 and come out with a nice number and add it to 1 and clean that all up if I want. But whether I do or not, I can't change this into a logarithmic equation until I get rid of that. How can I get rid of that $1,300 on the right? What do I have to do to get rid of it? Be careful. Not that careful. We have to divide it out. We can't subtract it. We've got to divide it out. Okay. Oops, wrong place for the comma. So what does that give me? Let's see. I get what? 21/13 equals 1 plus 0.09 over 4 raised to the 4t power. Okay. Now, I don't want to round off until the end, which is why I left it as 21/13, because that does not come out exact. But if I take 0.09 divided by 4, I get 0.0225, which I could then write as 1.0225 to the 4t power. So I've got 21/13 equals 1.0225 to the 4t power. Okay. I can change that into log base 1.0225 of 21/13. Oops, I wrote 13 backwards. Equals 4t. Are you following?
Yes.
All
Yes.
right. So now I've got to either divide both sides by 4 or multiply by 1/4. I'm going to multiply by 1/4. So now I've got t equals 1/4 log 1.0225, base of that, and then 21/13. Okay. 1/4 is 0.25. And then I'm going to use the change of base. Let's see, put these in parentheses. So now I'm ready to punch that whole mess into my calculator. But before I do that, any questions about any of the steps?
No.
No.
All right. So 0.25 log of 21 divided by 13, close that up. Divided by log of 1.0225, close that up. I'm getting 5.388314, etc. Let's see. This one, we're going to round to the nearest 10th of a year. So that would be 5.4 years approximately. Right with that?
Yes.
Okay, let's see here. Is that one, that one? Let's do one more. This says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. So A equals A sub 0 times 2 to the negative T over H power. We've got T and H and A sub 0 and A. In 2 years, so the time is 2 years, 20% of a radioactive element decays. So the starting amount is A sub 0, 20% decays, so the ending amount would be 80% of the starting amount, or 80% of A sub 0. Okay?
Yes.
And the unknown is the half-life. So our equation becomes 0.8 A sub 0 equals A sub 0 times 2 to the negative 2 over H power. We're going to divide both sides by A sub 0. 0.8 equals 2 to the negative 2 over H power. We're going to change this to a logarithmic equation. Log base 2 of 0.8 equals negative 2 over H. Now, I'm trying to solve for H. H is in the denominator, so getting rid of the negative 2 on top won't do it. We've got to get, that would be 1 over H. We need H on top. So what I'm going to do now is multiply both sides by H. Okay. So now I've got H log base 2 of 0.8 equals negative 2. But I need to solve for H. So now I'm going to divide both sides by log base 2 of 0.8. So H equals negative 2 over log base 2 of 0.8. Using the change of base formula, H equals negative 2 divided by log of 0.8 over the log of 2. All right. Now, I can do this as it is, but if I'm going to do that, I need to quantify that whole thing. So in my calculator, or on my calculator, I'm going to put negative 2 divided by, and then I'm going to put a parentheses, log of 0.8. I'm going to close up that parentheses, divided by log of 2, close up that parentheses, and then close up the whole thing. So I'm going to come back to that screen in a minute. This is what is in my calculator. So there's this set of parentheses that's around the whole thing, and then there's this set around each of the two things. So this whole thing here, and I get 6.21. Let's see, what did they do here? They rounded to the nearest 10th, so about 6.2 years. You okay with that?
Yes.
Yes.
Any questions? All right, so your new formula is this one. So tonight, again, you're going to have a few problems from 11.6, change of base to get used to that. And 11.7, chapter review. Tomorrow, we'll do a chapter review. And then Wednesday, no class meeting, just the test. Come back on Thursday and Friday, we'll review for the final exam. I'll be back this afternoon at 1:15. If you've got any other questions, I'm going to stop the recording.